Hello everyone, in today's video we're going to cover section 10.8, the power theorems. After studying this section, you'll be able to apply the power theorems. The power theorems are three theorems that we'll use to help us find the measures of segments of a circle. So the first power theorem we'll look at is the chord-chord power theorem. Theorem 95, if two chords of a circle intersect inside the circle, then the product of the measures of the segments of one chord is equal to the product of the measures of the segments of the other chord. So here, product of the measures of the segments. So if I look at chord SL and chord VN in my figure to the right, I can see that they intersect at point E. So if I say LE, and then the other part of the segment would be SE, this would be one entire segment SL, and that's the product. This is equal to the product of the other segment. So VE times EN. So the chord-chord power theorem tells me that the two segments, LE times SE, is equal to the other two segments, VE times EN. Now looking at two examples of the chord-chord power theorem, we have my figure to the left. One segment is 26. The other segment would be 8 plus x. Now these are two chords. They intersect, so I can use the chord-chord power theorem, which tells me the product of the measure of the segments of the chords that intersect is equal. So I would have 20 times 6 is equal to 8 times x. 20 times 6 is 120, 8 times x is 8x. I divide by 8 to get me x is equal to 15. So the length of my other segment is 15. My figure to the right, I have this segment intersecting with this segment. So the product of the segments, 15 times 20, would be equal to 26 times x. 15 times 20 is 300. That's equal to 26x. I'll divide by 26. This one's not nice, so we'll just round to the nearest tenth, which would be 11.5. So x is 11.5. Our next power theorem is the tangent-secant power theorem. So if a tangent segment and a secant segment are drawn from an external point to a circle, then the square of the measure of the tangent segment is equal to the product of the measures of the entire secant segment and its external part. So what this is telling me is the whole tangent secant squared, so TP squared, is going to be equal to the whole secant segment, so RP, times the outer portion, PQ. And again, this is the tangent-secant power theorem. Looking at this in example form, we have a tangent segment here, x. So this is going to be x squared because the tangent segment is equal to the secant segment multiplied by the outer portion of the secant segment. So the whole secant segment would be 6 and 7.5, which would make 13.5. And then the outer portion is 6, so 13.5 times 6. X squared will be equal to 81, and x is equal to 9. So my tangent segment is 9. And our last power theorem is the secant-secant power theorem. If two secant segments are drawn from an external point to a circle, then the product of the measures of one secant segment and its external part is equal to the product of the measures of the other secant segment and its external part. So what this is telling me is that if I have secant segment here PB, PB times its outer portion, which would be AP, will be equal to the other secant segment, so PD, times its outer portion of PC. So PB times AP is equal to PD times PC, and this is the secant-secant power theorem. Looking at an example of this, we have two secants, and we want to find this length C, so the inside portion of my secant. Now I know that secant-secant power theorem tells me that the whole segment, so this whole segment is 20 and 11, which is 31, times the outer portion of the segment, so 11, will be equal to the other segment, the whole segment, so that would be 13 plus C, times the outer portion of 13. So I'll just write this as 13 times 13 plus C. Now 31 times 11 will give me 341, and then 13 times 13 plus C would be 169 plus 13C. I'll subtract 169 from 341, which will give me 172. That's equal to 13C, and then if I just round to the nearest tenth, I'd get C equals 13.2. So the inside portion of my secant is 13.2. Now, to summarize our three power theorems, we can see these three diagrams. Figure 1 was our chord-chord power theorem, which told me the product of the chords are equal. So A times B is equal to C times D. My second figure is secant-secant power theorem, which told me the whole secant segment times the outer portion is equal to the whole secant segment times the outer portion. And then my third figure is tangent-secant power theorem, which told me the tangent secant squared is equal to the whole secant segment times the outer portion. Now looking at our sample problems, we have problem 1, find x, y, and z. So example A, we have chord-chord power theorem. I know in a chord-chord power theorem, the products of the chords will be equal. So 6 times 2 will equal 3 times x. So 12 equals 3x, so x is 4. In B, we have a secant tangent power theorem. I know that the tangent segment squared, so y squared, will be equal to the whole secant segment. That would be 16 plus 2, which is 18, times the outer portion, which is 2. So y squared equals 18 times 2, which is 36. If I take the square root of 36, that gives me a positive 6. So y is 6. And C, we have two secants, so secant-secant power theorem. I know the secant segment times the outer portion is equal to the secant segment times the outer portion. So if I look at 8 and 4, the whole secant segment would be 12. 12 times the outer portion of 4 would be 48. That's going to be equal to the whole secant segment of z times the outer portion of 3, so 3z. So 3z will equal 48. I will divide by 3, so z will be 16. Looking at problem 2, we have tangent segment PT measures 8 centimeters. The radius of the circle is 6 centimeters. Find the distance from P to the circle. So let's start with drawing our circle. We can draw in tangent segment PT. PT is 8 centimeters, and my radius was 6, so this portion is 6. I'm looking for the distance from P to the circle, not to the center, so this distance here, which is x. Now I can extend my radius to make it a full diameter, which would be 12. Now I've created a secant and a tangent, so I can use my tangent-secant power theorem. My tangent-secant power theorem was the tangent segment squared is equal to the whole secant segment, so x plus 12, times the outer portion, which was just x. 8 squared would be 64. X times x plus 12 will be x squared plus 12x. I want to move my 64 over to the other side so I can factor this. So I'll have x squared plus 12x minus 64 is equal to 0. What multiplies the negative 64 and add to 12? That's 16 and 4. So x plus 16 and x minus 4 will be equal to 0. Setting them both equal to 0 and solving would give me x is equal to negative 16 and x is equal to positive 4. I'm going to throw out the negative 16 because I can't have a negative side length. So x, the outer portion, the distance from P to the circle, is 4 centimeters long. In today's lesson, we learned to find the lengths of the segments of a circle. We can use our power theorems. That's a wrap on today's video. We'll see you in the next one.